In this video lesson, we're going to be looking at single displacement reactions. So like we've done with the other types of reactions, we'll start off with a definition and a general formula. So a single displacement reaction is a reaction in which a single element reacts with a compound and the element takes the place of one of the elements in the compound. So it's going to replace or displace one of the things in the compound so that it's now part of the compound. So what it looks like here is if we have an element A reacting with a compound BC. Okay, so this is your element plus a compound where A is going to take the place of either C or B, depending on if it's a metal, it would take the place of the metal, or if it's a non-metal, it would replace the non-metal. So in this case, let's assume A is a metal. In this example, it's going to replace the metal in the compound, which in this case would be B, because the metal always comes first when you write a chemical formula. So that would give us AC plus B. If A was a non-metal, so on the side here, if A equals a non-metal, then we would get BA plus C. So in that case, A would be a nonmetal, would replace the nonmetal in the compound, which would be C. You get a metal and a nonmetal plus a new nonmetal out on the side. And we're going to look at examples of both of those. So here we have a special little resource that you get at the back of your periodic table called the metal activity series. With the metal activity series, okay, elements can only replace another element that is lower than it on the periodic table. Okay, so the least reactive metals are closer to the bottom. Okay, so least reactive down here, the most reactive are up here. Okay, a reactive metal will displace or replace any metal that is below it on the activity series. Okay, so let's do an example. The first type here is when a metal replaces another metal, okay, which is when we're using this metal activity series. Here we have the compound silver nitrate reacting with copper. So silver nitrate has the formula AgNO3. Okay, and this would be aqueous, so dissolved in water, plus copper. Copper on its own would be Cu, and it would be just a solid piece of copper metal, like a piece of wire or a penny or something like that. When we look at the list over here, we'll see that copper is right there and silver is below it on the periodic or on the metal activity series, which means that copper is able to replace the silver. Okay, so it's more reactive. It's going to bump the silver out and pair up with the NO3. That's going to give us copper. We'll say copper 1 nitrate, so CuNO3, aqueous, plus the silver is going to be out on its own as an element. So metals, when they're single elements, are solids. Okay, let's finish the word equation now that we have the chemical equation, which is already balanced. So it's good to go. I often find it's easier to do the balanced reaction equation before doing the word equation. So here we've got copper 1 nitrate. So copper is a multivalent metal. You have to include the Roman numerals. plus silver. Let's do another example. Here we have aluminum nitrate plus iron. So this would be AlNO3 aqueous. All of these ionic compounds in these types of reactions are going to be aqueous. So they'll be in solution, dissolved in water. That's what that means. So the aluminum has a charge of 3 plus, the nitrate is 1 minus. When we crisscross, we get aluminum nitrate like this, plus iron. Iron is Fe. When we look over at the metal activity series, we can find iron is right here, and aluminum is up here. So in this case, the aluminum is higher than the iron. So the iron is not going to be reactive enough to push the aluminum out. So when that happens, when the single element is lower on the list, okay, there's going to be no reaction. Okay, so nothing's going to happen. The iron's not going to be able to bump out the aluminum. The second type is when a nonmetal replaces a nonmetal. So this is more like this case over here in terms of a general formula. And the activity series that we use for nonmetals is here. So it's basically the order that it appears on the periodic table. So these are your halogens, okay? Fluorine, chlorine, bromine, iodine. And when you can kind of think about it, when you look at the periodic table, fluorine's at the top, then chlorine, then bromine, then iodine. As you go down on the periodic table, that's the order in terms of the activity. So the stuff down low is least reactive, the stuff at the top is the most reactive. And the same rules apply. Only things that are higher on the list can bump out stuff that's lower on the list. So here, if we look at chlorine plus calcium bromide, chlorine gas is Cl2. So these are all part of Hofbrinkel, those diatomic gases. So they're always going to have the 2 subscript and the gas symbol. Plus calcium bromide is CaBr2. Okay, and this would be aqueous. So calcium bromide, calcium has a charge of 2 plus, bromine is 1 minus, crisscross, that's how we get the subscript 2. Now in this case, we look at chlorine and bromine. Chlorine is higher than bromine on the list, so it's going to be able to boot out that bromine to form calcium chloride, CaCl2, plus bromine gas. So we write out the word equation. We're going to get calcium chloride plus bromine. Or you can write bromine gas if you like. Let's do another one. Here we've got iodine plus calcium bromide. So iodine is I2 gas plus calcium bromide, we already know that one is CaBr2 aqueous. Here we check the activity series. So the nonmetal activity series, we've got bromine and iodine. In this case, iodine is lower than bromine on the list. So it's not going to be able to displace the bromine because it's not reactive enough. So for this example, there would be no reaction. Now there's one final type of single displacement reaction. So we've looked at metals replacing metals, nonmetals replacing nonmetals, and this last type is looking at the displacement of hydrogen by a metal. So this is a metal replacing a nonmetal, but the nonmetal in this case is hydrogen. Hydrogen's a little special because when it forms an ion, it's a positive ion. Okay, we get H+, so hydrogen is H+, rather than all the other nonmetals form negative ions like chlorine and bromine and oxygen. So a metal, okay, is positively charged. Hydrogen is positively charged. So metals are going to replace hydrogen in some special cases. Now hydrogen is difficult to displace and only certain metals are reactive enough to do that. And the way that we know is if we look at hydrogen on the list here, Okay, it is in with all the metals because it forms that positive ion. Anything above, okay, so metals higher than hydrogen can displace it from an acid. So an acid is a compound that contains hydrogen. So this would be like nitric acid, hydrochloric acid, hydrofluoric acid, all kinds of acids. So anything higher than hydrogen on the list can replace hydrogen from an acid. So here's an example of one of those. So magnesium plus hydrochloric acid. Magnesium on its own is just Mg solid. Hydrochloric acid is HCl. Acids are always aqueous. Magnesium is higher than hydrogen on the metal activity series, so it's going to be able to displace that hydrogen out. So the magnesium replaces the hydrogen and we get magnesium chloride, aqueous, plus hydrogen gas, so H2 gas. The word equation for this is magnesium chloride plus hydrogen. If you were to react something lower on the metal activity series with an acid, nothing would happen. There wouldn't be evidence of a reaction. Next, last example is sodium and water. Now, water is a special case. It's not an acid, but we can displace hydrogen from water, but only for group 1 metals. So here we'll see potassium and sodium are there. So only group 1 metals. So that means metals in the first column of the periodic table can displace hydrogen from water, H2O. Okay, so sodium, lithium, potassium, rubidium, all of those. Okay, anything else, if you put any other metal in water, it's not going to react. And that's a good thing, because when you think of all the metals that we put in water, like if you're making a dock or a boat or something, we don't want things randomly reacting with water. But our group 1 metals are particularly reactive and they can displace hydrogen from water. So an example here, if we look at sodium, we've got Na, solid. Sodium is a soft silver metal that it's very, very soft. It's kind of a bit like cheese in terms of its hardness. So sodium plus water, H2O, is a pure liquid. The sodium is going to replace the water, but it's going to form a base. So it's not just going to form sodium oxide. Really, that is what's happening. It's forming sodium oxide, but remember what we learned about synthesis reactions. As soon as you have a metal oxide in water, okay, it's going to make a base. So think about it like if it does swap over, if you had Na plus H2O, and you are making NaO, Na2O plus H2 gas, but then this is still, there's lots and lots of water, it's in excess. So it's still in water, it's still in H2O. So really you're getting NaO, Na2O plus H2O, and you're forming sodium hydroxide, which is a base in water. So that's that metal oxide plus water makes a base thing that we saw in synthesis reactions. So when we talk about the single displacement of group 1 metal and water, basically we're going to go straight all the way to this base plus hydrogen gas. So we're forming sodium hydroxide plus hydrogen gas. Now sodium hydroxide is a base, so it's going to be aqueous. And then we need to balance this one because this one's not already balanced. When we look at hydrogen gases, we've got 2 there, but we've only got 1 there. But our only source of hydrogen is in the water, and it comes in 2s. So we need this to be an even number of hydrogens on this side. So we'll put a 2 out in front of that to give us a total of 4 hydrogens. Here we can make that 4 by adding a 2 in front there, and that will also balance out our 2 oxygens on both sides. Then we need 2 sodiums on this side, so we can add another coefficient there. And that's it. We'll do some practice questions in class tomorrow. See you then.